Good morning, everyone. Thank you, Luke, for the introduction. Today, I will introduce to you E3SM Diagnostics with focus on enhancement in version 2. Other than our main developers, we have a strong support team tailored to support E3SM Diagnostics from E3SM Unified. With Charlie's NCO support, we are able to offload intensive computation to NCO as pre-processing steps. Sterling has been supporting our users who access E3SM Diagnostics through process flow, and many from the project also contributed. E3SM Diagnostics is a modernly designed Python-based diagnostics package being actively developed for supporting E3SM model development. The primary goal is to be able to bring analysis and data sets identified by science groups quickly into our routine analysis workflow. Initially, the evaluation sets were modeled after NCAR's AMWG package, and we mostly focused on atmospheric variables. Adding for land and river variables is ongoing. The package has a number of features I'd like to highlight. It is flexible to add new observational data sets and diagnostics and to modify aspects of the figures. It's a Kanda package, therefore easy to install. Configuration and execution steps are straightforward. The program runs fast with multiprocessing. And lastly, the provenance of runs is saved to allow for reproducing diagnostics figures. We aim to stay up to date with observational data sets so that newer and better edition of OBS will be used in our evaluation. E3SM Diagnostics also supports CMIP-style monthly time series data. Therefore, it can be used as a community tool. This slide shows current diagnostic sets available. The first milestone of E3SM Diagnostics was to complete the key basic sets as those from AMWG package. As shown on the left side, we now have implemented lat-long map accompanying with tables and Taylor diagrams summarizing metrics from the lat-long maps, pressure versus zonal mean and pressure versus meridional mean plots, polar maps, zonal mean line plot, and cusp joint histograms. Each 3-panel plot often composed of test data, reference data, and the difference between the two. The reference data could be observation or another model run in the model versus model configuration. Either pre-calculated climatology files or monthly time series files can be used as input of these core sets. On the right-hand side, moving on to version 2, we now have support for time series analysis, ENSO Diagnostics, and QBO diagnostics. These new sets take monthly time series as input. For input data requirements, there is sometimes some confusion. Unlike NPAS analysis for ocean, E3SM Diagnostics only takes data on regular lat-long grids. Therefore, one has to process the raw EAM output into climatology and time series files using NCO. Provided here are the NC-climo commands and the resulting file name examples for climo and time series files, respectively. Note that make sure to specify uppercase O. This will place the regraded files in the directory separated from the native grid files, but the files have the same names as native grid files. And the directory with regraded files will be passed into our configuration scripts. Most users often only look at core sets. In this case, have seasonal climatology data processed is sufficient. For first-time users, we recommend you to use the example data from our data server. to try out the diagnostics package. For users have Linux or Mac OS machines or would like to install latest version of E3SM Diagnostics that is not yet supported with E3SM Unified, here is the instructions. First step is to install Miniconda and initialize the Conda environment. If you haven't installed Anaconda, Miniconda is a light version of Anaconda and only include Conda Python and some basic packages. Therefore, take smaller space and faster to install. There are two ways to create the E3SM Diagnostics environment. First is to create the environment through an environment YAML file. In the YAML file, all the versions of each dependencies are pinned down. This way, the installation process is faster because Conda doesn't need to decide versions of packages to pick up. The downside is that if any pinned down versions of package are broken, the installation method would fail. Alternatively, one can just create an environment using conda create. The example command line here used version 2.11, which is the latest tag we have for E3SM Diagnostics. The version number needs to be updated with future release. Once the new environment is created, active the environment with conda activate. Again, to set up E3SM Diagnostics on the new machine, you need to download the observational datasets and sample data files for testing. For E3SM groups who have access to E3SM supported machines, E3SM Diagnostics is pre-installed through E3SM Unified, which is a conda environment pulls together Python and other E3SM analysis tools. To activate this conda environment, one can simply source an activation bash script available on each machine. Right now, there is an NPI incompatibility issue with E3SM Diagnostics specific for Cori compute nodes. So please use the unified version with NPICH support for now. We will address this issue in next emergency release of E3SM Unified. In addition, observational data and example data for testing are already available on these machines. Next, I want to show the configuration process. In version 2 of the package, we introduced a new way to run, that is to use a clear interface to pass in parameters. Although version 1 configuration is still compatible, to run the newly added stats, the new interface is required. On this slide, it shows an example run script to pass in parameters for core sets using pre-computed climatology files. In this configuration Python script, all required parameters are set up through a param object. The required parameters include data paths for reference data and test data. Test data name often is the case name of an E3SM run. Selected seasons, the result directory to save output, including the HTML files. Here I use a path on Cori, where the HTML pages can be served online to share with others. Multiprocessing and the number of workers are set for parallelized run. Without setting these two, the run will be just in serial. In terms of timing, on Cori Haswell with 30 processes on one node, this config takes about 4 minutes. Some useful parameters are listed here but commented out for this configuration. By default, the test name is being printed as the title of test data plots. The short test name is useful when the test name is too long or a different name for plots is desired. The run type needs to be set for model versus model run. The default is model versus ops. Title of difference plot can be renamed. Use diff title. The output figure format can be configured to be PNG, PDF, or SVG. If output format subplot is specified, the subplot of 3-panel plots can be saved individually. When save netcdf is set to be true, the data being plotted will be saved as the netcdf files for reproduction of figures or additional analysis. At the end of the script is to specify the sets to be run. You can pick and choose from any of these listed sets. In this script, we are running all the core sets. Last line is to pass in the parameter object in E3SM Diagnostics runner. The next run script is for all sets configuration. Compared to the core configuration, here we need to define additional parameter objects for individual new Diag sets. The setting for core parameter is the same as earlier. Continue the configuration script. For each of the new set, the data paths are changed to use the directories with the time series files. And the start year and end year are used to set up for selecting the time segments from the time series files. In this example, we use the same time period for each analysis and for both test and reference data, but they can be set differently. Lastly, the new sets are specified and the additional parameter objects are passed in to E3SM Diagnostics runner. By walking through this run script, we can see that allowing each new analysis to have an individual parameter space offers large flexibility to introduce new and more complex diagnostics. For instance, to add support for land and river components for Diags using sub-monthly data. Again, with 30 processes on one Haswell node, the wall time is about 70 minutes for this configuration. This is a simple guide for running this configuration on Cori Haswell. First, you will SSH to Cori and then download our tutorial example using wget from our GitHub repository. And you will need to edit this script. The only change is to change the results directory to somewhere that you have written permission. And it is recommended to use a compute node to run multiprocessing program. So you need to request a node from Haswell. The debug queue is much shorter, so I recommend to use partition debug for trying out. Then if you have E3SM Diagnostics environment installed, you can just do counter activate the environment. Alternatively, you can source a pre-installed E3SM unified environment. Lastly is to use Python. Next, I want to walk through the E3SM Diagnostics viewer and show some tips getting information from it. Here shows the main page of E3SM Diagnostics viewer. The diagnostics results are grouped by sets. At the bottom is a link to provenance. In the provenance folder, we provide the command line to run and the environment YAML file and the configuration script to run. From the configuration script, you can find where the data is located and you can use the similar configuration to reproduce a run. This is the main page for latitude-longitude contour maps. The plots are grouped by observational sets and seasons. There's a drop-down menu in the middle that you can use to jump from different observational data sets. And clicking on the season name, then you will arrive to the 3-panel plot for comparing seasonal mean climatology between test and reference data. At the bottom of the plot page, there is a section called Output Metadata. E3SM Diagnostics can run using command line. Here shows the command to reproduce a single image. So you can edit this line to refine the image. For instance, if you feel the contour levels are too dense, you can change the contour levels. And make sure to change the results directory name so that the original output view was not disrupted. Next, I'm going to present our progresses since last all-hands meeting. We implemented 2 components of ENSO diagnostics, which were identified as critical for ENSO DIACs, including maps on regression coefficients of atmospheric fields over SST anomaly and scatter plots of atmospheric feedback on SST anomaly. QBO DIACs is implemented based off Yaga's 2019 paper. This set includes 3 components: QBO index, amplitude, and the spectral intensity of zonal wind. Quarter-degree ERA5 data with 37 vertical levels are used here, which have enough levels above 100 millibar for this analysis. This is our first implementation of DIACs from community. Thanks to Chris Terai, he was able to follow through our developer's guide and help the implementation. Most recently, we have the initial RRM support ready. The lat-long plots are adjusted to be able to zoom in on the region. The CONUS RRM domain is predefined. Other RRM regions can be easily added in the future. And quarter-degree ERA5 and 1-degree GPCP observation are used for higher resolution visualization. The command to run this special config is put in here, and I also put a link to the example output that you can walk through after the presentation. We have several developments happening in parallel. These are 3 items that are major. We are working with TN on implementing the runoff and streamflow DIACs. This will be our first set touching on land and river model output. Charlie is building a diurnal cycle climatology capability into NC-CLIMO. We will use pre-calculated seasonal mean diurnal cycle of precipitation as a recommended option for this set. We are also working on integrating the ARM data-oriented diagnostics to enable comparison to ground-based high-frequency observational datasets. These 3 sets already demonstrated their usefulness in model evaluation in the past. And having them in E3SM Diagnostics will greatly facilitate model development. And we also have a list of new sets being planned and requested. For instance, tropical cyclone analysis, stratospheric ozone diagnostics, dust aerosol analysis, precipitation intensity, and atmospheric CO2 diagnostics and metrics. The wishing list is getting longer, so to speed up the development, we hope more developers will join us. For how to contribute, there are a couple of ways to contribute. First is to put in a future request and to share the data sets and a Python-based script, including instructions on data preprocessing with us. If you are an advanced Python developer, please maybe try to follow through our developer's guide on how to add the new diagnostic set. If the guide is not applicable, or if the required infrastructure support is not available yet, we will help with providing skeleton codes and provide infrastructure update. And at the end, we will have a few rounds to do final touch-up and testing. So hopefully with this procedural, we can have we can see the diagnostics you want to use in the E3SM evaluation workflow routinely, fastly. Okay, that's what I want to talk about for today. So I'm happy to answer any questions.